Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so today we're just taking a little bit of a break from my Class A amplifier, which I'm still going to build. Just waiting for parts, okay guys? This box has been sitting around staring at me. It came from Gan Systems, and it's a Class D amplifier. There's two boards in this box. One's a power supply, one's the amplifier. This is really cool. I'm really excited about this. It's a new design, and let me just tell you about some of the specs real quick here. Okay guys, look at this. Now this from Gan Systems. This is an eval that they sent me, and it was free. So a lot of times on the job, vendors will give me eval cards so that I can evaluate them, so I can see if I like the parts on them, and they'll usually put them in a circuit so I can see how they work in that circuit. And they give them to you free because, you know, it's the easy way for us engineers to take a quick look at them, see if they work before we take the risk of putting them in a new design that we're working on, okay? Well, I've got this YouTube channel. I've been lucky because I've been getting some eval cards, and this one is an expensive one. It's over $900 on Mauser. That's really cool. I didn't know it cost that much until I went and looked it up because I was doing some research on this after I got it. I want to say it's not a sponsored video in the sense that when you say sponsored videos, that's usually when you're getting paid and agreed to do a video or a review of a product. And I haven't been sponsored, so I don't know if there's any strings tied to those or not. I don't know how they work, but I have been given eval cards. And the difference is I'm not getting paid to do it, and they just send it to me, and they just let me do what I want with it. Okay, there's absolutely no strings tied. And even the equipment, you know, where I've gotten a power supply, or, you know, I have been given a few pieces of equipment, you know, same kind of thing on those. Where a sponsored video, you're actually making money. A lot of us YouTubers, we don't make any money at all. We're, you know, it costs us a lot more in our time and so on to do videos. So anyway, we do it because it's a hobby and we like to, and it's fun to, you know, get the feedback and work with you guys. So anyway, enough said there. So you've had a chance to probably read all this stuff. It's a 2-channel Class D, 200 watts continuous. This is continuous into 8 ohms, 2 channels. Or 300 watts into 4 ohms continuous, okay? And it's a bridge tied load. So, you know, basically you have a bridge, you know, 2 transistors on each side of your speaker, you know, where you're going to tie the speaker. And so it's a bridge tied load. The power supply capable of 400 watts continuous, so it can do the 200 watts per channel continuous, and it can go up to peak 550, which that's nice. That's quite a bit of peak power for the power supply. Okay, but here's some of the cool features. The power supply is going to put out plus minus 32 volt rails, and because of the design of this, it's actually, even though everything's switching Class D, the power supplies are all switching power supplies, it's still EMI friendly, EMC friendly, because they're somewhat soft switchers, okay? So that means there's not a lot of sharp edges, not a lot of noise, not a lot of EMI. And one thing you have to think about is, we know a Class D amplifier is very efficient, works off these DC power supplies, very efficient. But when the power supply working off AC power can also be very efficient, well, there's not a lot of energy to waste in EMI. So a very efficient power factor corrected power supply should be more EMI, EMC friendly, okay? And this one is. And guess what? The cool thing is all this power, continuous power, no heat sinks. So how's it do it? Well, the hint is GaN. They came from Gan Systems. That's that GaN FET. I've done some videos, the future of power electronics, GaNs. I've done some other Class D amps. I'm going to put the links below so you can check those out. Go in more detail about GaN and so on. But okay, so that's what we got here, guys. And there's 2 boards in here. I'm going to open up these boards. I'm going to show you the circuits. But before I do that, I just want to talk a little bit about that no heat sink thing. I'm going to take my Coilcraft magnifier here, let's just say this is a MOSFET or a transistor of some kind, like a GaN or a MOSFET. Well, most transistors that we see, right, if they're through-hole or surface mount, there's a metal tab. So let's say this is the die, the semiconductor. They put it on like this substrate that sits on this metal that's going to get soldered down to your board or put up against a heat sink. And then this side's a plastic case, right? So you have a transistor TO220 or something like that. Looks kind of like that. So there's some thermal resistance between, the metal here that goes to the heat sink. If you put a thermocouple here and a thermocouple on that die, you're going to see a temperature difference, and that's the thermal resistance. So the smaller you make that, the better you can cool that die. So you want to transfer all that heat as fast as you can to the heat sink. Okay, GaNs do that much better because the packaging is much simpler. The die, the substrate, is practically what you're soldering to the board. So it makes the packages very small, low inductance, and a lot of good things come from that. And one of the good things is that thermal resistance is probably at least half as much as a MOSFET. Okay, so pretty cool. Literally. Alright, so once they do get hot, they transfer the heat better. Okay, what's the other thing about them? Well, there's a couple different ways to get losses. Let's talk about that on my board. Okay guys, so here's my little picture here of the FET turning on and off. Okay, so the voltage on the drain is here, it gets turned on, and I exaggerated this ramp time. Comes down here to almost 0, but there's a little bit of voltage there because of the current times the resistance, the RDS on, and then it ramps back up and it's off again until the next cycle happens. You get 2 switching losses, two of those, and one of these I squared times R, RDS on times whatever current is going through the transistor during that time. So here's the power dissipated. So MOSFET compared to a GaN, this guy here is going to be 3 to 4 times higher. This guy here is going to be 8 to 10 times higher, let's say. Anyway, overall you're going to be easily 10 times more power lost on your GaN than a MOSFET. Now the MOSFET might cost 5 times less than the GaN device. So it's like, well, what the heck? I'll put a heatsink on it. Okay, well, if you solder to the board and you have a heatsink on the board, or if you use the metal chassis that the board's going to get interfaced with somehow, maybe through a thermal pad, well, you got to add that gap pad. If you have a fan blowing, a heatsink, you're paying for all that stuff. And then also labor. Let's say it's a stand-up part. Let's say it's a through-hole part, stand-up part on the board, and you're going to mount it to a heatsink. You're going to mount some old big old heatsink like this, okay? Well, if you do that, now you got to put washers, isolation devices probably, maybe some pads, some thermal grease. Oh, and also there's the assembler. I'm going to have to sit there and assemble it, so you're going to have to pay me to do that too. So you're putting money into things to help cool it versus putting the money into a really cool transistor that stays cool. Alright, so now here's the thing, is you're saving this kind of power and that by going to GaN. Another thing you have to remember is because it's GaN, more ideal switch. Well, with the Class D, as you're switching on and off, and you've got a top transistor and a bottom transistor, or say in the power supply as well, in any kind of bridge type device, or lots of types of converters where you have a freewheeling FET like the Active Clamp 4 that I showed in the previous video. There's lots of devices where you have 2 transistors toggling on and off, and as you do that, you have to program some dead time in there because of these ramps. And not just because those ramps, actually, guys, something that people kind of forget, unless you're that guy actually doing the design work, is when the message to that transistor says turn on, there's delay time before this ramp even occurs, okay? And then same thing, if let's say for instance you're monitoring the current, and as the current slopes up, you're saying, okay, right there, turn off. Well, there's dead time where nothing's happening. Just, you know, digital electronics, anything, there's time that happens before the signal transfers from like, oh, I'm going to do this, to the time when it starts to do that. Okay, and so you got that that dead time in there. All right, guys, that was bugging me. Propagation delay is the word I was trying to think of, but I don't know if, I think in FETs, transistors, they just call it delay time, but it's like in any kind of chip where there's propagation. The control chip's probably going to be propagation delay, and then it goes to the FET, and there's some delay time in the FET. With the GaN, those times are less, okay? Much less. The switching cycles are much faster, on the order of, say, 10x, okay? So what happens is, when you're designing it, you don't have to build in so much dead time, so you can turn on and off and bring those cycles from the top transistor to the bottom side transistor. Instead of having that built-in delay time between them, you can pack those in closer together. Another thing to think about is the MOSFET. I should show one here, but it has that body diode across the FET. You know, it's just, there's nothing that they really wanted to have in the MOSFET. It just came with the packaging. When you designed a MOSFET, it just turned out you had a PN junction from drain to source. It wasn't what they wanted, but they were kind of stuck with it. In the early days, what they did is they made that a better diode to actually be more robust, so you could actually use it as a diode. But yeah, anyway, that just kind of comes along with a MOSFET. And again, it doesn't have that. It's a different, it behaves in a similar way, but it's completely different structure inside the GaN, okay? The advantage of that is on a MOSFET, because it's an actual diode, a PN junction, there's a reverse recovery time, because during that delay time, those body diodes will be activated and turn on. But well, then you have to turn those guys off. Well, there's overshoot. There's some losses in that body diode too that we didn't really talk about. That gets starting to get complicated. But I just bring it up just to say that there are all these other factors that come into play, and that's why it's not magic that there's no heatsink. Short story. There's a reason there's no heatsink, and there's a reason that the cost of the GaN might be worth it. You do the trade study and you take those considerations in, where your circuit's going to actually work better. Let's say in a Class D amp, there's some switching noise in there, okay? And you'll have some feedback loop to counteract that, and you can get some really low THD figures with a Class D amplifier, no problem there. This design, we'll have to look to see how it's done, but they allow you to do open loop to show you that this guy actually works well enough, low, you know. And when they call THD plus noise plus N, which I can do that over here on my Keithley meter too, the THD, we know what that is. That's harmonics of the frequency, the fundamental frequency. If it's a 1 kilohertz, for instance, test waveform, 10 kilohertz, it's multiples of that, even multiples. Well, if there's other noise that's in between those frequencies, that's not really counted unless you do the plus N. Well, in a Class D amplifier, if you do the plus N and you do feedback, you can keep that figure pretty low. I mean, low enough. I mean, plenty low enough, okay? But one of the advantages with the GaN is that it's easier to maintain those figures. And so, from what I understand on this eval card, we'll have to get into it and look, see how that's done. But you can operate open loop so you can compare, and it's supposed to be pretty impressive. So, alright, let's get, alright guys, one last thing before I open this box. Let me show you something else. Alright guys, one more time to the board. There's two cards, but the power supply is really two stages, I think I've mentioned before. Power factor correction. As the current's being pulled in, instead of like a so-called linear power supply, where you go through a bridge rectifier, you store voltage on a capacitor. When the diodes get forward biased, there's a pulse, a real big peak pulse current coming through. Well, with power factor correction, you're trying to bring in a little bit slice of current all the way around that sinusoidal voltage waveform, so the current draw looks sinusoidal as well, and it's pretty close to the same phase as the voltage too. So in the case of a normal power supply, there's a parent power, what it looks like that's going in. You monitor current, monitor voltage, you go like, well, there's 100 watts going in, but that's called VA because it's volts times amps. The actual real power might only be 40 or 50 watts, 60 watts, because it's so bad. The current and the voltage are so, badly put out of phase. But with power factor correction, or active power factor correction, where you have a circuit, a boost converter in this case, that's actually trying to control how much current that comes in as a sinusoidal waveform builds, it makes the current look sinusoidal, and that also makes it look very clean for EMI. And then you come to this LLC, which is an inductor capacitor stage, and that's a form of a resonant converter. Okay, so then after that you get isolated plus minus 32 volts. Now you don't have any ties to the primary power ground or return. Now you got your isolated plus minus 32 volts and come into class D. Now, one thing to go back here, the PFC, this voltage here ends up being, I have to see what it is on this design, but it ends up being close to 400 volts, like 380 volts, because it has to be above the peak of whatever voltage you expect it could come in. So if you think 220, so if this guy's going to work for universal input, say 220, then the peak of 220, you want to regulate that voltage above that peak, because you always want to be boosting, and you can't boost if your output voltage is less than your input voltage peak. Okay, so anyway, that's that stage. And in this stage, isolation, plus minus 32 volts. This stage, your class D amplifier. This one's on one circuit card, this is on the power supply circuit card. Okay, let's go look at the cards. Alright, so here's our box. And see, this scene says that we have the bundle. We have the amp and the power supply. Alright, first thing we see is a cable. Okay, there's the cable. 6 wires. Fairly kind of stiff, but anyway, I assume this is the cable that goes from power supply to the class D. So it takes the power, but it's got 6 wires, so I'm not sure why. This one has a red heat shrink, so maybe that means something. Okay, let's delve into this and find out. Alright. There's some tape here we got to get by. Okay, there's one card. There's the other card. Big one, small one. This looks like it kind of looks and feels like a power supply. Let me look. There's the power supply. So I see neutral, ground, and line. And then this is given our isolation barrier between primary power, I suppose, but it's interesting it goes all the way up here, and secondary power. This has to be the boost, and then going out here. So as we flip it over, we can see, okay, wow, nice capacitors. Okay, and the power supply. This is very interesting. The input power comes here. Fuse, that's an MOV. Couple yellow caps or white capacitors. Then it goes to the next capacitor. It says WE. That's Worth Electronics. I almost thought that was a WEMA, but that looks like Worth. And then it looks like 2 common mode chokes. And look, some more white capacitors and XX. So these are cross line. X are across the line, line to neutral. And white capacitors are line to ground and neutral to ground, earth ground. Okay. So this is the EMI filter right through here. And then it looks like we go through, it looks like 2 bridge rectifiers, which is a little surprising. Instead of using one big one, they got 2 in parallel, it looks like. And then we have another X capacitor, this gray one. I can't see the value, but I'm sure that's an X capacitor, poly. These are all polypropylene, I'm sure. And then we go into our boost inductor. Looks like a single winding. See that? One winding going around that thing. So that has to be our boost inductor. And this must be our control chip. We'll take some close-ups, but wow, that's a thermistor. Looks like this black guy that's kind of bent over. Okay, that's just on some skinny leads. I don't think it was meant to be bent over. That's a 0.047 resistor. That's probably a current sense resistor. And then alright guys, and then amazingly, that is our FET. Look how small that thing is. That is teeny. That's crazy small. Then we have some big, that looks like a diode, a Schottky diode probably. That's a big part there. I'll have to take a close-up of that. So it's right underneath our main boost inductor, our main boost circuit, our FET, and our control chip. I'm sure that's it. I'm thinking that this is probably the diode that charges the capacitor strapped across the parts, and we'll have to take a look to see what this guy is. And you can see these large ceramic capacitors. Those are nice. A couple more big ones over here. Those are huge. So over on this side, yeah, we have these big transistors. We'll have to look, see what these are. These might be diodes. This is a diode here. This might be a diode too, or a FET. Looks like they're tied together. I'll have to do some reverse engineering. This could be a FET that's going to short out this diode after it gets turned on. A synchronous rectifier. So if we look at this side, which over here, so power comes in, our boost, and over this side, and then look at those two guys. Those are our other GaN FETs. Look how small they are. It's crazy. It's just nuts. No heat sinking. And then look, a couple big old ceramic capacitors, and then this is this must be our LLC transformer. So our boost inductor, our LLC, and then these are diodes. These are big diode packages. So this is one rail, this is the other rail. We look over, see, look, more diodes, and these look like inductors. So we have some LC filtering going out to our output, and there's a chip here and a chip up here and a chip here. Yeah, not sure what all these guys are. I have to do some reverse engineering to find out what's going on here. But it looks like basically we have our input fuse, our over voltage protection MOV, our EMI filter, bridge rectifier, our boost circuit right here, and then our LLC power supply right here, coming out to the output of the LLC to our plus and minus voltage rails. These are 50 volt rated, and we're supposed to have plus minus 32, so that sounds like a good D rating. Alright, these guys here are 400 volt, 33 microfarads. These four guys. These are 400 volt. These guys are 400 volt, 56 microfarads. Yeah, I'll have to do a little reverse engineering and I'll come up with the schematic for next video. And here's another Y capacitor straddled across the see this line here? It's this line here, right through the transformer down here. So this is our isolation barrier. This is our primary side, right here. Input filter to the boost converter, and this is our transformer right across here. So that's very interesting. Then our output comes back to our, man, look how small that board is. 400 watts, guys. There's 400 watts right there, AC to DC. Pretty dang nice. Look at the size of that. Nothing too tall, nothing too big. Looks, I'll have to look, see if I can find the artwork, but that to me looks like maybe 2-layer, maybe 4-layer at the most. Wow, nice design. Alright, let's open up our amplifier. I'll keep our power supply on top so you can see it. Wow, look, there's our amplifier. Plus, there's 200 watts per channel, 8 ohms. Doesn't look like much there. A bunch of aluminum electrolytics, some small inductors here, and some output inductors here, just because they're big. They have to be. And our output connectors. So, and look, some poly caps here. These might be mylar or polyester. These are probably polyester type capacitors output. Some aluminum electrolytics, lots of aluminum electrolytics. But man, there's a big, look at that big chip right there. There's a big chip. Bunch of op amps possibly, maybe a bunch more op amps. I can see maybe some transistors here. You're looking at it with me first time. Interesting. I'm not sure what these, oh, those are switches. Oh, okay, they feel like push button switches. Now, this came with optical input and RCA input, at least. And I think there might be another type of input. Here's a little connector here for hooking up some software to configure things on the chip. Okay, there's our EAS. There's a big microcontroller. Another big old chip by this connector here. But look at this side of the board. Pretty bare. Not much there. Not much at all. I see some capacitors, some more small parts through here. And then another controller or some kind of chip up here. Oh look, next to these switches. So there's some kind of controller up here. Alright guys. We have some standoffs so you can stand the board up without damaging things. RCA connector here and here, I think. Now, actually, that looks like a right and left in a video, I guess. That's weird. I'm sure that's for something else, some audio. But, and this is a volume control, it looks like, right here. Can't, you know what? That's a digital control knob because, yeah, that's a digital pot there because it just spins. And some other audio connector there probably. And here's your opto connector right here. Man, I have to look at the documentation that came with this to see what we have. Okay, let's see if I can get a close-up of some of this stuff. Okay, there's our bigger chip right there, guys. With the label, I'm kind of wondering if I'll be able to look that up. It might be made specifically for GaN, so... But look at these chips here. I'm guessing op amps, transistor. There's our input section. Big old inductors. Here's our output section. More transistors and I'm assuming op amps. I'll see if I can do some reverse engineering. Alright, flip the board over. There's one output. Another output up here. Yeah, the board, there's a lot of vias where signals and temperature is dissipated and pulled through the backside of the board. Here's the other control chip in the corner here, near the input section. There's another one. Not sure what those guys are. I have to see if we can do some reverse engineering here. Let me know if you guys know what those things are. Hey guys, one thing I found out is this connector right here, this pin here is tied to this red guy. And the way it's wired, because I was trying to find which connector went to what, but the way it's wired is it doesn't matter. Either end I plug in, the red wire is on this pin. So that's good. So that means it's ambidextrous. That means I can plug it in either side. Now one thing I did notice is, see this on the amplifier board, the red's up here? Well, that red wire I just got through showing you on that pin, no matter what, it plugs in to the red side. Because there was also red on this, the power supply side. So they kind of made the power supply connector red and the audio amplifier red, and then they put the red heat shrink on the cable. So looks like they connect like that. Yeah, so it looks like they connect like that. And I just have to find a power connector, input signal, and output to the speaker loads. Alright guys, so there's our two boards connected together with the cable. And we will plug them up and test them out next video. And also, well, we'll see what we do next video. I think we'll do some audio testing, we'll do a complete unit. And then if we have time, we'll break it down separately, test, or we'll do another third video. Hey guys, so what do you think of that? Just didn't want to keep it too long. Just wanted to introduce it this time so the video is not like an hour long. Because the next video, please watch, because we're going to power this bad boy up. So I'm impressed. That's a 400 watt power supply, 550 watt peak. It's pretty cool. EMI filter, the whole bit, all on that card. No heat sink. That's impressive. Okay guys, and the other thing that's impressive is your amplifier board, right? I mean, they've left it open for testing and the back side's really empty, so this could be made much smaller. But you know what? It's just impressive because that's 200 watts and 8 ohms per channel, 2 channels. So 400 watts. Or 600 watts into 4 ohms. Continuous. No heat sinks. That's crazy. That is just crazy. And I don't think I've pointed them out because they're so small. I looked right over them, but the transistors are under my fingers right here. 2, 2, 2, and 2. So there's 8 transistors across here. That's just... wow, I just look at them, I'm like, really? How do you do that? It's efficiency. It's the way they operate. It's just nuts. I can't wait to power it up. Okay, let's do that next video. I'm going to do that very soon. Okay, guys? Hey, let me know what you think. And thanks for watching. Thanks, Patreons, for all your support. Thanks, everybody, for watching the videos. And I thank you guys for all your comments. Those are really nice. I like to see them. Right now, I'm still able to keep up with all the comments. So I'm happy about that because I'm almost 5,000 subs, which kind of blows me away, guys. Geez. Yeah, 6 months ago I had 1,000. It took me a year to get 1,000. Well, 10 months to get 1,000. We're almost 5,000 now. So by the end of the year, let's hit 10,000. That'd be super cool. But there we go, guys. Buck Cherry. I love this concert, by the way. Had to wear a music shirt for a music video, right? Okay. Have to find another one for next video. Okay guys, we'll see you next time. Thanks for watching.